Hi everyone, joining this call or
Yeah,
joining this
yeah,
video on Learn with Meshach, where we talk about how we apply machine learning principles, artificial intelligence, and other techniques to agriculture and environmental sciences. So today, I'm having Krishna on the call to share with us the Python package that he built for agriculture, and the Python package is called geeagri, and it's a Python package for agricultural modeling and analysis using Google Earth Engine. So he's going to be sharing with us about it and also demonstrate some functionalities of the package or some functions of the package that you can use in your own work process to ensure that you achieve the best and yeah, make progress in your agriculture and environmental science analysis. So I will hand over to Krishna now to go ahead with the demonstration and talk about the package so that we can understand it. Krishna is a geospatial data scientist and working with AI for agriculture, remote sensing, and earth observation enthusiast at the same time, and is currently resident at Zalf in Germany. So yeah, over to you, Krishna.
yeah. Thank you, Message, for the nice introduction. Yeah, okay. So I can share my screen first.
Yeah,
Okay, okay. I think it's visible now.
yeah, good.
Okay, so this is a Python package that we recently developed at SAL and for agricultural analysis using Google Earth Engine. And I have been working in this field like remote sensing for like 2 years. And what like I have found that this like field is you need to prepare a lot of data like if when you are dealing with remote sensing. And so I started with manual scripting. Then I thought that okay, if we can build a package and then we can build some kind of functions that will help you to download the data easily, like large scale down data sets. Like if you want to download time series data, if you want to download image data for deep learning workflows. So then we developed this package, and I can give you some examples of this package. Now you can see that the main functionality of this package is currently data extractions, and it extracts the data quite well from Google Earth Engine, but we are currently extending the data extraction process from Stack as well. So we are working on it so that it can extract the data from Stack. Now you can see that this is the time series extraction, and you can also open it in Colab. So if I open this specific notebook in Colab, so this is for time series data extraction from Google Earth Engine, and using this you can extract climate data, you can extract NDVI time series if you are building any time series model like LSTM or some sort of GRU, uh, uh, or maybe transformer architecture. You can use this and extract large scale time series data from Google Earth Engine. Also, this one is for image patch extraction. This one, like if you are like training some vision models, like vision transformer or CNN models, you need satellite data, and then you can use this. It will help you to download the data in specific patches, and you can set the size of the patches also, like 256 by 256, 512 by 512. It's very easy. And then it has some analysis capability also, because what I have seen, like if you want to implement harmonic regression or principal component analysis, you need to like write a lot of codes in Google Earth Engine. It's not so straightforward like you what you did in Python using scikit-learn packages or any other packages, but in Google Earth Engine it's a bit different. So therefore, I just wrapped the harmonic regression logic into this single class, which is harmonic regression class, and you just need to put your image collections, and you can get the harmonic coefficients just by in 2 lines. Similarly, it has some gap filling techniques inbuilt. So if you want to like do some satellite gap filling or cloud gap filling, then you can use this moving window smoothing, or you can use this time series gap filling. And also it has some regular time series. We know that satellite time series is not a regular time series like climate data. So if you want to create a 5 days interval time series for Sentinel-2, you can use this notebook, regular time series, and it will create like uniform interval time series for satellite data. And also I implemented one land surface phenology module in this. So it gives you some sort of start of the season, end of the season, and length of the season. So this kind of land surface phenology variable using satellite data, and it's very easy. So internally, I am using Savitske-Golay filter. So this is also you can use in this package. Okay, so just for an example of time series data extraction, so you can see that I first of all you need to install this library. So I think
Yeah, you
okay,
can zoom the Google Colab so that we can see the code clearly in the video.
yes,
Yeah,
yes,
I think it's good now.
yes. So first of all, it will take some seconds to install the library, and so this I have taken as like example ROI, but you can change the ROI. You just need to put your bounding box here, and then it will extract the data for you.
And by ROI is region of interest.
Yes,
Yeah.
yes, yeah,
So if the region of interest is India, if the region of interest is Germany, if the region of interest is even a field somewhere in Germany, you just need to get the bounding box
yeah,
and sometimes maybe the shapefile also, right? Or the coordinates
yeah,
of the
yeah.
area. Yeah.
Yeah, you can do that also. And then here you need to authenticate first. You need to run these cells, and here you need to provide your project ID from Google Earth Engine. Okay, so it's done. Then I can create the map. Okay, so here you need to provide your bounding box, and I'm just converting it into a polygon. And also you can give your latitude and longitude. So
So
if
do
you're
you want
giving
to
a
show what the
region,
map looks like?
it maps, it's just a
Yeah.
global map now. I
Yeah.
didn't add the region of interest so that I need to run this cell.
Okay.
But so, okay, so if you are giving a region, then you need to give a reducer. So if it is a region, you can define the reducers. You need to take the average of that region. You need to take the sum of the region. So it's up to you. You can give a reducers based on your choice. But if you're giving a latitude and longitude, then it will just pick the raw data from the dataset.
Nice.
So as you can see, this is a region and this is a point. So if you give the point, it will pick the values from that particular pixel. But if you give the region as your area of interest, so it will take the mean or median as per your choice. So, and now you can see I am taking the ERA 5 collection. So it's a climate data set. It's a daily climate data set. And I'm taking one single variable, so like the temperature, but you can specify different bands also. It's up to you. And this is the resolution of the dataset. It's around 11 kilometer. And now, so I have created some samples here inside the region. And here I need to just run this. And here you can see that I am like extracting the data for these four variables because we crop modelers need these variables quite a lot because temperature minimum, temperature maximum, precipitation, and solar radiation. And you
Yeah.
can define the start date and end date. So I am extracting the data for 10 years. It's a daily time series. It's quite long, but if somehow it fails in your case, then you can reduce the like range of the time so that Earth engine has some limits in, so you can reduce the range of the time also if you're getting some error. And you need to specify a directory also where the data will be saved. So, and this also you need an identifier column. So here what I am doing here, I am extracting data for multiple points. Okay. So I have around 97 points. And for all of these points, I have IDs because the data will be saved by this name, the ID name. So you can, so currently I'm using like 97 data points, but if you have more data points, like 1000 data points, you can also use that. It's not a problem. So if I do this, I need to just pass my data frame, geodata frame, 97 data points, then the era 5 data sets from Earth Engine. Then you need to specify the bands. You need to specify the output directory. You need to specify the identifier column, which is this ID. You need to specify the scale and also the number of processes. It's a parallel processes and the start date and end date. And then you just need to perform this ts extracted dot extract time series. And now you see the data is getting saved. And I think it will be saved in this test folder. So you see, and if I open any of them, you see,
Mhm. That's nice.
yes, and it's pretty fast. It's pretty fast. I think it will take like 1 minute to save like 100 time
So it will
series.
take like 1 minute to extract 10 years data.
10 years data for 100 points. 100
Yeah,
points.
400 points. Yeah.
Depends on the server speed also, but I think it's quite fast. Similarly, here I have given example for, I think, then what you can do, this is for batch processing. You have multiple points, then you need to use this. You need to provide your GDF geodata frame file. But if you want to download for only single point, then you need to provide lat and long. And yes, I think it's done. Yeah, it's done. So it takes near about 1 minute. For single point, you just need to provide the latitude and longitude. And if you have a single polygon, you can provide a polygon. And here, as I said that for polygon, you need to define a reducer. So here I am taking the mean, but you can also choose median or standard deviations, whatever you need on that region. I think it will also extract the data.
Yeah, that's because the polygon covers a specific area. And for that specific area,
Yes,
you need to be able to define like, okay, how much pixel does that area cover? And you need to take the reducer, maybe the mean of that whole area or the median of that whole area. That is what you want for, yeah, the data
yes.
of interest. Yeah.
Don't know why it's
Can you still hear me?
Yes. So one is I think temperature minimum and one another is temperature maximum. So this is how you can extract satellite time series or climate data time series from Google Earth Engine easily. So now I want to show you how can you extract image patches for your computer vision workflows if you are dealing with satellite data. So I will open this notebook now. Sorry, I can open it in a new window. Okay. And it's very interesting. So I have used this quite a lot. Like I when I
Sentinel,
use some
Sentinel 2.
CNN, yes, you can use Sentinel-2, you can use Landsat, whatever you want. It should be an image. So now again, I will install the package and the class name is image patch extractor. And here I just paste an URL, which is a high volume API of Google Earth Engine. And it enables like if you want to extract large scale Earth observation data from Google Earth Engine, I think you should use this URL because it's a high volume API. I think in one request, API request, you can extract 32 MB data. So it increases a maximum data size that you can get from Google Earth Engine. So, and then you need to provide your project ID. So I will put my same ID here also. Okay. Okay. So I need to first authorize it.
So, and the reason you had to do the authentication and installation is because every time you open Google Colab on a fresh project, it is a new instance. So, and for the new instance, you need to install the packages that are not the default package of Google Colab. You need to always reinstall them whenever you start a new Google Colab instance. So that is why the installation had to be done again in the image patch extraction.
Yeah.
Yeah.
Yes. So here also I just imported I think the same region of interest and so this is the scale factor I'm applying here and then I'm clipping it in for the region. So it's a median composite image of 2024 and then you will get a nice false color composite image here. Yes, it should come and okay. So now let's say from this email from this region, yeah. So now you can see the false color composite. Now let's say I need to generate some random points inside this region, and you need to extract the data in patches. So I don't want to extract the whole image, but I want to like split this image into different chunks, and then I will extract those patches. So what you can do here, you just need to sampling over your regions. So see, I am creating 100 pixels here, and I'm taking a buffer because you create number of different like a large number of points, let's say 100 points, and you take a buffer, and I'm taking buffer of 2 kilometer, and then so just let me plot it first. And all these points will fall inside this region. Okay? And this is the main function. So I can explain all these parameters it takes. So image, it will take the Sentinel-2 image, the median composite image. You can change it based on your choice. And then you need to provide the sample GDF. Here I am just creating an example geodata frame for those points, specific locations, but you already have some region of interest. You can just replace this variable with your geodata frame. And then also you need to define an identifier column. For each of those points, there should be a column that can be the parameter by the same ID. And then you need to define the output directory. Yes, now we have around 100 points. Because for all of these points, you can take a buffer and then you can extract a patch. And its dimension is based on your model configuration. You can choose it. If you want to run your model at 256 by 256 image patches, you can use 256 by 256. It can be 512 by 512. And then the format. So by default, it's a geotip, but you can change it to PNG or JPG also. But as you know, that geotip, you can extract multiple bands. But for PNG, it will be only RGB. So if you want to extract different bands, then I think you should go with geotip. And also here the number of processes, it's also parallel processing, so it is quite fast. And if you run this, so it will hit the API and then download all these images. Yes, see, it started downloading the images, and it's also quite fast. So if I go here, yes, so images folder, and you can see all these images, but you cannot open it, obviously. But you can open it in QGIS after downloading the data. Okay, so I have already created this script to randomly plot some images. So let's see, let it be finished, and then we can plot the data. And this is very helpful for vision model training. Okay, so by the time we can keep another demonstration of harmonic regressions. It's a if you want to implement harmonic regression in Google Earth Engine, you need to create like write a long code, and I just wrap all the logic in a single class. So I will open it first. Okay, so same thing again. I need to install geeagri. So before that, I just need to give you some sort of introduction of harmonic regression. So harmonic regression is a technique where you can like compress a time series informations. It's based on Fourier transform. Basically, it's a Fourier transform technique. And let's say you have a time series, and you can summarize this time series into different components. So it's basically you fit some curve, some time series curve in your actual time series, and you get the phase and the other coefficients also. And just basically you're representing your entire time series into few different components. And it's very useful because if you are training a model with a complete time series of satellite data, and it would be so large, so you cannot train a model with a heavy time series data. So what you can do, first you apply harmonic regressions on a time series, get the coefficients. You will get only three to six coefficients, and use that coefficients to train your model. In this way, you are basically summarizing the entire time series into six different coefficients, and it's very efficient. If you want to train your model faster, you should do that. But you cannot use a whole image time series to train a model. Like if you have 60, 70 time steps, it's very heavy then. Yeah.
Yeah, so
So
basically it can help us to understand pattern, extract a specific pattern in the data set.
like principal component analysis, what we do in principal component analysis, let's say you have 12 bands, then you apply PCA on it, you transform your dimensions, and
Yeah,
you just reduce the dimensionality of the data, like from 12 bands, you after that you will get three bands, but that three band has no meaning. It's
exactly.
basically you just summarize the data in a format which is very handy,
Exactly.
like in three bands. So
Yeah.
so similarly here also you cannot understand the meaning, but
Yeah.
you just reduce the dimensionality of your time series into just three components. So that's the idea.
Yeah, yeah, yeah. So
Okay,
so basically,
so
so instead of having the 365 days, which of course, which has meaning intrinsically, so it might give, that was where the time step idea was coming from. It might give this kind of time step that is just six, but it doesn't mean they have specific meaning. But the algorithm can still learn from the data. So that is like how it works, especially also with PCA at the same time. So the algorithm can really learn from the data. Same with, for example, if you use also like convolutional neural network embedding sometimes, you can do that kind of thing also. So it doesn't have meaning directly itself, but the algorithm can learn the pattern within it. So that is, yeah, that is the idea.
okay, so just to plot this, because our images has already saved in the specific folder, so you can plot it and see how it looks like. So yeah, see, this is the ID of each of the points, and it just gets saved with the same name, same ID value, and these are the images. And now you can use these images and train your vision model. It's it's pretty simple for the data preparation task. So you need a mask also. Let's say you are doing some land cover classifications and you already have, you can use the cropland data layer from US, or if you're working on Europe, you can use some land cover data set that is already there in Google Earth Engine, and also you can extract patches of that land cover data sets, and then you get the satellite image and also the label, and you can train your model. It's pretty easy. So, okay. Now coming back to this harmonic regression, so I just plotted the map. Now I need to define a region of interest. And here, just to, for example, I'm importing the cropland data layer from US. Yes. So now you can see the different crops. I think this color is for maize. No, sorry, I think it's for winter wheat. This yellow one is for maize, and this green one is for soybean. Okay, so now for all these crops, there will be slightly different phenological. You can find a difference in phenological time series. So you can. So here, what I am doing is I'm in like taking the Sentinel-2 image, and this function also you can find it in geeagri. It gives you like you can do efficient cloud masking using this function. So you just need to define the start date and end date. You need to define your region, and you need to specify the thresholds here. So it's the cloud filter. I'm taking the 60%, and this is the cloud probability thresholds. I'm taking 50%, then dark threshold, shadow threshold, and also the buffer. So you can define this threshold, and your time series, your image collections will be cloud mask. So here, this is the functions from this class. So get cloud free collections, and this is our cloud max time series. So if I just print it, you will see that this is a time series, and the data type is Earth Engine image collection here. Yes, so it has 48 images, and this is basically a time series. So it's starting from January 2020, then you have February, March, April. So this is an entire complete time series. Now, what we will do, we will summarize this time series using harmonic regression. So before that, we need to maybe we need to calculate some index. I don't need all these bands, let's say. So therefore, I want to calculate NDVI for all of these images. And now we have NDVI collections, and I can also print this NDVI collection. So it might take some time. It depends on the server, but I can just restart it, I guess. Yes. So see, we have same 48 images, and now we have uh, only the NDVI band for the time series. And on this time series, we can apply harmonic regression. And for harmonic regressions, you need to specify a reference date and your band name and your order. So order is 3. That means you are basically fitting a third order equations. So you will be having 3 components. If you fit two second order, so you'll be having 2 coefficients. So something like that. And the omega is the cycle. For that, I think you can refer to the harmonic regression logic in Google Earth Engine. It's a quite long theory, but it can just implement it by using this easy class. The harmonic regression, and then you get the harmonic coefficients,
So this
and you
this
get the
this
sign.
harmonic regression here is coming from GEE. This
It's
class
coming
that you're
from
using
GEE.
here is coming from GEE, right?
No, 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 no. This is from geeagri.
This that's what I'm saying.
I
G,
just
I mean GEE agree. I mean, it's coming from the package. That's
yeah,
what I
yeah,
mean.
yeah,
Yeah, exactly.
yeah. It's coming from the and uh, so that's it. You just need to use these 2 lines and you get the phase and amplitude. So in harmonic regression, you get phase and amplitude. You can plot it. So you can basically summarize the time series using phase and amplitude. And also you can get a hue saturation value image. And let me plot first, and then I can show it to you how it will look like.
Mm,
Okay. Yeah, see. Now let's say you are doing crop classification, okay? And these are the crops you have in your region of interest.
mm,
And if you take only the phase image, see, for each of the crops, you can have a different color and you can easily identify different crops. If you
mm,
run on any unsupervised model also, it can easily detect different crops and different crops is having different colors.
mm,
And this is the phase. So this phase represents the peak of the time series. And for each of the crop also, you will find a different value in phase and amplitude also you might find a different value for it. But this is very important, this phase amplitude image. This is a like RGB image in a single band. In the 3 bands I'm using this combination phase amplitude and I think value. Let me check. uh, yes, I think, yeah, phase amplitude HSB. I think I need to go to this function and see the logic. I don't remember what are the bands I'm using in the RGB color space. But this is what you get after the harmonic regression. So you just summarize your entire time series into a single image, single hue saturation value image, and you get a image that you can use for the crop classification, and you can easily identify different crops here. So it's pretty useful.
that's
So
interesting.
this is all about harmonic regressions, and yeah, and if you see the code provided by Google, it's a quite long code. So what I have done, I have just wrapped the entire functions that Google has provided into my geeagri and just created this class so that it makes I just like implemented it easily so that it's useful for user also. They can extract harmonic regression easily. And also, I don't want to go through all these things, but you can explore if you want. And we are also adding some new features. Uh, right now, we are working on Stack, so maybe in couple of months we can have these features also, so you can extract data from Stack as well. This
Wow.
is work in progress.
Wow. This is very interesting. Thanks a lot, Krishna. So if you're watching this, so feel free use geeagri to make your workflow very smooth and to do things better. And if you're a beginner and you are seeing all the code and it looks like something complex, if you check some of the other videos on my channel, I've introduced to Python, to some data processing and other kind of videos that could help you. And I'm continuously uploading other videos also that could help you as a beginner get started with applying machine learning in agriculture and then environmental science. So thank you very much, Krishna. So hopefully, when you add more features to GE Agri, maybe I'll invite you on the channel again to talk about other projects that you'll be doing and also the advancement in GE Agri. And
Yeah,
I
yeah,
believe, of
sure.
course, you will respond because the
Yeah,
viewers watching this right now, they would love to probably see you again to explore some things and also maybe to explain other concepts in deep learning,
yeah.
especially for agriculture and remote sensing and all. So maybe we still have another time for that. So I would say thank
Yeah,
you
so
very
just
much.
one more comments from my side for
Yeah,
the viewers. If they want to like contribute to this package, so I'm quite open to it. So they can
nice.
also improve the package. Yeah. And if they found some issues or bugs in the package, they can also like put their comments in the issues so that we can solve it. And that's thanks, message for for inviting me. And yeah, hopefully I'm also working on different projects, so different packages as well. So we can also discuss those things in some time later.
Yeah, that's amazing. So thank you very
Thank
much,
you.
Krishna. So for everyone watching this, like the video so that other people can see, so that the algorithm can push it for others that could benefit from it. And also subscribe so that another time you can see videos where Krishna is teaching a concept from a package or from machine learning and deep learning at large.
Yeah,
So yeah, and also share around on LinkedIn and other platforms where you could see people that are interested in things like this and so they could benefit from it. So thank you very much, Krishna, and have a wonderful time
thank you.
in Zal.